number 11, is that C is going to be the curve of intersection of two planes. The first plane is x squared equals 2y, and the second plane is going to be 3z equals xy. So you're going to find the curve that is the intersection of two planes. So you can imagine this one might be like a quadratic plate going upwards, right? And this one is some weird, curve going like this. And it would intersect with this guy in some kind of peanut shape. So the first piece of the puzzle is to find the intersection of these two planes. So I'm going to take x squared equals 2y, and I'm going to make I'm going to make x equals t. Now, if I make x equals t, then that means 2y will be whatever x squared is, which makes y 1/2 x squared, which makes y 1/2 t squared, because I chose that guy. So the trick to doing these types of questions, where you're looking for the intersection of two planes, is to pick somebody to be x, or somebody to be t, in which case I'm picking x. And once you've picked him, then this relationship allows me to get y in terms of x, which now means that y is 2t squared. And now I should be able to get z. If 3z is equal to xy, then 3z was going to be t times y, which is 1/2 t squared. So 3z is going to be 1/2 t cubed, which makes z 1/6 t cubed. So all I need to do is find typically x equals t, that then lets me get y in terms of t, which then allows me to get z. And now I have my space curve. It's t 1/2 t squared 1/6 t cubed. Now, if I decided to make one of the other variables my t, I would have got an answer. It just wouldn't have been a space curve that looked like this guy. So the first part of the question was, find the space curve that is the intersection of two planes. And we're done. And then what they want us to do is find the exact length of the curve from the origin to a point in space called 5, 25 halves, 125 sixths. So when they're saying exact length, they're really saying arc length. And they just don't want decimals. So the arc length is going to be the integral from a to b, the magnitude of the derivative, dt. Well, I've got a few things I need to get here. They didn't tell me t equals, and they didn't tell me t equals. I need to figure out what t value gets me the origin from this space curve, and what t value gets me this guy from this space curve. Okay, let's look at this one, the origin. Would you agree that t has to be 0? If I want this space curve to be at the origin, won't t have to be 0 to make that happen? Okay. Here's the finish point. The guy that's going to be B. What value of t generates this point?
Five.
Okay. So my arc length formula is going to be the integral from 0 to 5 of this guy, right? Well, I know who this guy is, so I should be able to differentiate him. Shouldn't I also be able to find the magnitude of it? And once I have, I'll plug it in here. So let's see what the derivative of the space curve over here looks like. Well, it's 1 t and 1/2 t squared. And if I want to get its magnitude of this, it's a square root of 1 squared t squared and 1/2 t squared squared. So it's going to be 1 plus t squared plus 1/4 t to the 4. Now, you know you want this to look pretty. Do you see a perfect square? Okay, I think this is the 4th one we've done today. Smallest, middle, big power, right? So they're in a good order. I can use this order. This guy gives me the guy that goes here. The end one gives me the guy that goes here. And we should make a perfect square then. What goes in the first place?
1.
1. And what goes in the second place?
1/16 t squared.
Oh, almost. I'll take
Oh
t
no,
squared.
1/2 t squared. Jeez,
There you go.
squared it.
You went in the wrong direction. But you were darn close, right?
Yeah.
And because it's a perfect square, don't we have a nice guy? I mean, it's actually quite easy to integrate that guy. So now that I have this fella, I'm putting it in here. So it's going to be the integral from 0 to 5 of 1 plus 1/2 t squared dt, which is what? T add 1 to the power divided by the new power, evaluated at t equals 5 to t equals 0, which gets me 5 plus 1/6 5 cubed. Take away a whole load of zeros. That's 5 plus 125 sixths. That's 30, so that's 155 sixths, which is the right answer, so I'm happy. So the trick to doing this question was to realize that you can find the intersection of two planes, this plane and that plane, by taking the equation that only has two variables and making one of them t. And it doesn't matter which one, but if we make x equals t, because that seems to be the going guy, then you can find out that y would be 1/2 t squared. And then you can use the x and y in terms of t to get the final guy, z. And now you have your space curve, the x, the y, and the z. And from the space curve, we can find the arc length. And that involves us finding the derivative, which is this guy, getting the magnitude of it, which came out to be actually quite nice. And then evaluating the integral to finish, to find 155 sixths. Right. there are only 11 questions there, and I am sure you're going to have to fight your way through half of them. About 6 of them, I think, are pretty straightforward. Right, there's not too much to do. And I'm not even counting question 11 as one of those. The ones you're going to have the biggest trouble with are the unit tangent, unit normal, unit binormal. They are just messy and ugly. And for those 5 guys that you're going to be dealing with, you better put away a half an hour for each of them. And you probably want to do maybe 1 or 2 and then have a break, just to give your brain a chance. And that is me for today, or tonight. So.
Do you mind going over
Mhm.
something from the last, like, how do you know when 2 particles collide? Like, I know that when the two lines intersect, because they can intersect at some point where they don't collide, right? The particles
Correct.
just pass each other up.
Right.
So how do you?
That's true, I guess on that one too.
Okay. Now, the difference between, let's call it R1 and R2. If you solve both equations where you make the variable t, and you can get a solution like t equals 3, then they will collide. If you make one of them a t, and you make the other one, say, an s, and then you solve, but in this case, you're going to get t equals 3 and say s equals 5, then they just intersect. If you get 2 equations where one of them's a t and the other one's an s, but t equals 7 and s is also equal to 7, then you have got to collide again. Because what you're essentially saying is at the 7-second mark, they're both at the same place, so they're colliding. What you're saying here is at the 3-second mark, the plane is here, and then at the 5-second mark, the other plane is here. So you know that thing when they do air shows where they cross over, but they don't hit. Collision, S and T are the same, even although the equations, right, use different variables. If the question gives you the variables both in terms of T, then you have to have a solution to this question where they collide. I think there was a homework question where when you made T equals 3, it didn't work. When you tried to solve it, you couldn't find a solution, right? It didn't work. But if you called this guy T and you made this one S, then you could find an intersection point. Does that make sense? A collision can only happen if the variable is the same number on both curves. So T are both 3, or T is 7 and S is 7, right?
Good.
If T and S are different, then they're intersecting, but they're not colliding.
Right. That makes sense because T would have to be the same.
Yes. And S is just a placeholder for time, right? So that would be an intersection, but this would be a collision.